Hi everyone, I'm David, and today I will tell you how to use ReasonML in your React applications. But first, just a couple of words about me. I have a Twitter, so you can tweet at me, coding_lawyer. I have a blog where I write about ReasonML, React, and JavaScript, codinglawyer.io. And I'm also organizing ReasonML meetups in Prague, and I'm contributing to Free Code Camp community. And I also work as a JavaScript developer at Blueberry, where we develop web and mobile applications using cutting-edge technologies. So let's get started. First question, who heard about Reason? Raise your hand, please. Cool, many of you. But today, I hope that all of you will learn something new today. But first, let's talk about React. React. It's one of the most popular ways to build user interfaces in JavaScript. So React, it's a pretty cool library. But could we make it even cooler, better? So who wants to write better React? Come on. Cool. Me too. But in order to write better React, we need to understand its problems. So what's the problem of React? Well, in reality, React isn't a native JavaScript library. I mean, if you take a closer look at it, you will see that some of its principles are foreign to JavaScript. Let's visualize this. Let's start talk about immutability. In React, we want to keep our stuff immutable. We don't want to mutate our props, and we don't want to mutate our state, because if we did, we would get some weird consequences. However, in JavaScript, we don't have immutability out of the box. If we want to keep our stuff immutable, we need to do it by convention, or we can use external libraries such as immutable.js or seamless immutable. Functional programming principles. React is based on functional programming. I mean, React applications are composition of functions. On the other hand, JavaScript, although it has some functional programming features, it's not functional programming language. Because if you really want to write some nice declarative JavaScript code, you need to, again, use external libraries, Lambda or Lodash-FP. Finally, type system. In React, we have prop types. And prop types, it's a way how to simulate static typing in JavaScript. Because JavaScript isn't a statically typed language. That means if you really want to write some nice static typing in JavaScript, again, you need to use external libraries. You need to use Flow and TypeScript. So if you take a look at our chart, you can see that JavaScript isn't compatible with React's core principles. So the question is there some other language that might be more compatible with React? Fortunately, there's ReasonML. Immutability. In Reason, we have immutability out of the box. Functional programming. Reason is based on Ocaml, functional programming language. Type system. Reason has strong type system. So if you take a look at our chart again, you can see that Reason is more compatible with React than JavaScript is. But let's talk about Reason. It's not a new programming language. It's an alternative JavaScript-like syntax for Ocaml, functional programming language that has been around for more than 20 years. So Ocaml serves as a backing language for Reason. And thanks to Reason, you can basically write Ocaml using JavaScript-like syntax you know. So thanks to this, in Reason, you can use all the cool features of Ocaml. You can use pattern matching, you can use type system, as we will see later. Now, compared to Ocaml, with Reason, it is easier to integrate it in your existing JavaScript code base. So let's take a look at the example of Reason code. Now, this is FizzBuzz algorithm. And although we are using pattern matching, which we don't have in JavaScript, the syntax is pretty similar to JavaScript. However, this is Reason, and the only usable language for browser is JavaScript. So we need to compile it to JavaScript first to be able to use it in the browser. And we can do that thanks to BuckleScript compiler. And BuckleScript will take your Reason code and compile it to readable and performant JavaScript with great dead code elimination. And because BuckleScript is based on the original Ocaml compiler, the compilation is really fast. It's much faster than Babel's compilation and several times faster than TypeScript. I mean, the compilation is really, really fast. Now, let's take our FizzBuzz algorithm and compile it to JavaScript. Now, this is resulting JavaScript code from BuckleScript, and if you take a look at it, it's pretty readable, right? I mean, it looks like it was written by a JavaScript developer. And it's a great advantage of this compiler because you get this nicely formatted code that's pretty good to read. However, BuckleScript also provides us with great JavaScript interop. This means that you can take your JavaScript code and use it in your Reason code base, and you can interact with that code. And you can do the same thing. You can integrate your Reason code in your JavaScript code base. And as a result, you can use all the JavaScript NPM packages inside your Reason code. That's pretty powerful. However, this talk is about React, so let's talk about React. We can use React in Reason thanks to Reason React library. Maybe you are still thinking, why should I use React in Reason? And we've already mentioned that Reason is compatible with React, more in JavaScript. But why? Why is it compatible? Because React was developed for Reason. More specifically, React was developed for Ocaml, because first prototype of React was written in standard ML. That's a language, it's a cousin of Ocaml. And then it was moved to Ocaml, and also it was transcribed to JavaScript for wider adoption. And this transcription, it really worked. We are now as I mentioned, React is pretty popular as a JavaScript library. But when React came into JavaScript, we need to adjust JavaScript to React's needs. We created a lot of tools and a lot of libraries that makes development smoother. However, as a result, this means another layer of complexity. It means many dependencies for our applications. So if we take a typical React application, we will at least have these dependencies. We have immutability, static typing, routing, linting, code formatting, and helper functions. Now, what if we swap React for Reason React? Do we still need all these dependencies? Immutability, we don't need it because Reason is immutable by default. Static typing, we have a built-in strong type system in Reason. Routing, we have a router built inside Reason React library. Linting, we have a built-in compiler that provides us with readable warning and error messages. Prettier, or code formatting. In Reason, we have a built-in Reason formatter that formats our code with a single possible way, so all the Reason code will look the same, because creators of language decide about that. And Lambda helper functions, again, we don't need them, because we have enough functions built inside the Reason. So if you write React in Reason, you won't need these and many other dependencies. And why? Because Reason is based on Ocaml. It's a matured language. All of its principles and rules how to structure your code in place and stable. So you can think of React in Reason as a safer way to write your React components. You have this strong type system, as we will see shortly, and you don't need to deal with JavaScript legacy issues. And I'd like to end this part of the talk by citing the creator of Reason and the creator of React, Jordan Walk. Reason is the best way to take React to the next level. Okay, now I hope you're pretty excited about Reason as I am. And now let's take a look at some code. I will use this tic-tac-toe game I built. You can get it at my GitHub, codingloader/Reason tic-tac-toe. But first, let's take a look how our game looks like. It's a typical tic-tac-toe game. We have a 3x3 fields, and two players are playing cross, circle, and they play till one of them win and one of them lose. So typical tic-tac-toe game, nothing really complicated. So let's take a look at the structure of our application. Now, this looks like typical React application. Just imagine it's our component tree, and these are the components. So we have an app component. That's the component that renders the game itself. Game is the smartest component. It takes care of our logic and of our state. And then game renders the whole board. Then we have rows. And finally, we have squares we can click on. So this is some general visualization of our app. And now let's start talking about Reason. more specifically Reason React. Components. In React, we can distinguish between stateless component on the one hand and stateful component on the other. And we can do the same thing in Reason React. So let's talk about stateless component first. We will use our top-level app component for that. So let's take a look. And first step is to define our component. And we do that by calling ReasonReact.statelessComponent and pass the name of the component. As you can see, we are explicit. We are saying this will be stateless component, and it's called app. And this component, it's not a class, and it's not a function. It's called record. And record is Reason's data structure, and it's similar to JavaScript object. But unlike object, so it's immutable. So you can think of it as an immutable JavaScript object for now. But this is a simple component, and it doesn't do anything. So we would like to adjust this component to our needs. And we do that inside the make function. And you can think of make function as a function that takes props and return your component, as in React. So first, because our component is not receiving any props, there's only default prop children that must be here, and the underscore means we are not using it. And we return our component, but we are spreading it, just as we spread object in JavaScript. So we would return a new record with additional properties. So we spread our component, and because this is a simple component, we would only add the render method. And render method takes single argument called self, but we can access state through it, but we don't have any state here. So again, we write underscore. That means we are not using this argument. And we get back JS6 as in React. So we have a capitalized element as a game, that's component, and uncapitalized like classical elements. So this is our stateless component. It renders the UI. It does nothing else. So let's take a look at a stateful component. In Reason React, we call them reducer components. And if you're familiar with Redux, this is a similar principle. Because if we are maintaining our local state in Reason React by Redux principles. So if you want to update your state in your local state, you need to fire an action that is catched by reducer, and reducer will update your state. Let's take a look at it. We will use our game component. As I mentioned, the smartest one. There's the whole logic of our app. And again, first we need to define it. Now we call the ReasonReact.reducer component. And again, we are explicit. We are saying it will be a stateful component. So we have our record. Then again, we go to the make function that takes props and return our component. But there are no props, so there's only default children prop. And we spread our component. And because this is a stateful component, we will add more properties to it. We will add initial state, reducer, and render method again. Now, initial state, it's as you can see, it's a function that returns our state. And you can see our state is, again, record, and there's board full of fields, and game state if we are playing, or it's a draw, or somebody already won. Then we have reducer, and for now, just take a look at the restart and the click square action. So reducer is waiting for these actions to be fired, and then it will do some behavior. And finally, we have our render method. And as I mentioned before, render method takes self-argument, single argument. But here we are structuring it just as we do in JavaScript. So we are taking state and send from the self-argument. And state allows us to access our state inside the render method. And send, it's a method, and it's similar to dispatch in Redux. That means if you want to update your state, you need to fire an action, and you need to call it with send. And finally, our render method returns our board component. And the most important thing here is this handler, onMark. As you can see, inside of it, we called click square with send. And as I mentioned, when we call send, we are firing an action. So just now, imagine that we are passing onMark to the board component. So from the game to the board, from the board to the row, and finally to the squares. And then when we are playing the game, we are clicking the squares. And then we click the square, so our action is fired. So we go again up from square to row, to board, and to game. And here, our reducer will catch the click square action that was fired. And we got the ID from the square that the ID is unique for the field that was clicked on. So let's take a look into the click square. Now there's some updating logic, but that's not important for us. Just take a look at this last method. It's called ReasonReact.update, and what it does, it purely updates your state. It means that there's no mutation, it will just return your state and update it. Now, you can't do any side effects here. This is just a pure state update. But of course, sometimes we would need to use some side effects. Let's say we would like to print click to cancel when you click the field. Well, in that case, we need to use different method. We need to use, for example, ReasonReact.update with side effects. And here we have two arguments. Firstly, we again update purely our state, and then we print using JSLog click to the cancel. Now, why am I telling you this? This is a really great feature of reducer component, because we have this clear separation between side effects on one hand and pure state update on the other. Now, let's think about Redux. In Redux, if you want to handle your side effects, you probably need to use some external library, such as Redux Tank, Promise Middleware, or Redux Saga to deal with the side effects. But you don't need to do this in Reason, because you have built this separation between side effects and pure state update handled by default. You have the methods that handle these distinctions. So this is pretty useful. Again, compared to Redux, it's less boilerplate. We don't need to define all those action and reducer files. And another great thing when compared to Redux, if we, for example, we want to write reusable React components. But when you connect your reusable component to the Redux global state, the reusability of your component decreases. And why? Because your component will be dependent on the structure of your global state. However, you don't have this problem in ReasonReact because you have your state encapsulated inside your component, so it's a local state. So you have this Redux principles inside your handling your local state and the reusability of your component. Now, let's talk about type system. Reason is statically typed language. That means it evaluates the types of your values during compilation time. This means you don't need to write your code to see if your types are correct. This is similar to what you know from TypeScript or Flow. Now, writing types means clearer and safer code because we have everything strongly typed. And Reason's type system is superior to what you get from Flow and TypeScript because it's built in, it requires much less maintenance, and you can rely on it on 100%, so this means no runtime exceptions in production. However, having a type system doesn't mean you need to write the types all the time. If you want to write your types manually, Reason will infer them for you and will figure them out for you. Let's take a look at some example. For example, here, this is Reason, but it looks like JavaScript, so you can see the similarity here. And we have a function that takes A and B and adds them together. And you can see we haven't write any types. But what Reason Compile will do for us, it will infer them. It sees that we are adding A and B together, so he figures out that they are all integers. And this is pretty powerful because you have this type safety on the one hand, and you still have this smoother development because you don't need to write types all the time. Now let's take advantage of types in our tic-tac-toe app. Now writing types will also force you to think in advance about your application. For example, we have a tic-tac-toe game, and in tic-tac-toe game we have two players, cross and circle. So we can define type player and say it will be cross or circle. Now, this is called variant or variant type, and you can think of them as of enums. They are enumerable sets of values. That means that player can be only cross or circle, but nothing else. It can't be string, it can't be a number, it will always be one of these two constructors. And we can also define another type. Again, we have our playing board, we have squares, and square is empty or marked. So we can define type field, and again, it's enum, and it's type or marked. And here you can see that we are passing the player, the type we've defined before, to the marked. And this is pretty useful because we can basically say the field is empty or marked, and it's marked by circle or cross, and nobody else. So we can build these more complex type when we passing the variance to another variance. And let's define another type called game state, and it's just the state of our game. So we are playing, we have a winner, or we have a draw. Again, enums. Our state of our game can have only these three states. Now, we will use these types we just defined in a minute using the pattern matching. But the last thing about types I'd like to show you is that you will get this really great developer experience because your favorite editor will provide you with great features such as code auto-completion or various hints. For example, here's a screenshot from VS Code, and we have some function called toValue, and it takes field as an argument, and then we name the field as a type of field we've defined before. And if you hover over it, you can see what we've just defined. That field is empty or marked. So again, smoother development, you don't need to check all your files. And combined with the fast compilation, the development is really a pretty great experience using Reason. Now, let's talk about pattern matching. This is really one of the most powerful features of Reason, and I will show you why. We will take a look at inside our game component. And we are still inside our click square method. Just for repetition, this is called when you click the square, so you update your state. And in this function, what we do is that just we iterate over all the fields, and then we check if the field is the field that was clicked on. And when we find the field we clicked on, we will do the pattern matching and determine the value of our field. But just a quick reminder, this is types we've just defined. They are enums: field, empty or marked, game state, playing, winner or draw, and nothing else. And our pattern matching we've just seen a minute ago. And now, in Reason, we use pattern matching to process our data. That means we have some data and define patterns, and then we match the patterns against our data. Let's take a look how this works. We use switch expression for that, and then we pass our data, and this data structure is called tuple, and it's Reason's data structure, and it's two pieces of data separated by commas in the parentheses. So our data is game state and value. And as you can see, they are both of the types we've defined. So game state, type of game state, and value, type of field. So we have our data, and we are now updating. Imagine that we click the field, and we are updating the value of the field. We will define the first pattern. And first pattern, we have a game state, and we set if the game state is of value playing. If it is, we have a match. Then we check the second pattern. If is field marked, and if it's marked, again we have a match. And this underscore means that we don't care about the player in this case. So we just care if we are playing and if the field is marked. And this is typically use case for tic-tac-toe game because you want prevent players from overriding already clicked fields. So if field is clicked and we are playing, we return original value because we don't want to change the value. Now, if this match fails, we go to another one. And here we again check if we are playing. Here we care about the player because we want to use it later. And if the field is empty. So another typical use case for tic-tac-toe game. We have an empty field and we marked it. And when we do that, we want to return that it's marked by a player who clicked the field. And lastly, we have a default pattern we need to write. And that basically catches all the other cases that might happen, and it will return empty. And this works because all our fields get disabled when one of the players win. But it's not important for this part. So again, let's take a look at our pattern matching. Why is it so powerful? We have this great combination of pattern matching and variance, because this can return only a single type, and in our case, it will return field value. So this can return marked or empty, but nothing else. We can't have any error that there will be number or string or anything else. We have this insurance. So basically, what this enables us to do, it prevents impossible states from happening. And it's pretty powerful because you don't have this if you do this with your if-else statements in JavaScript. And the second powerful feature of pattern matching is that let's imagine that we comment out the last default parameter. So that means we are not covering all the cases. And if we run the code, compiler will give us warning. It's telling us that our pattern matching is not exhaustive. And this is pretty powerful because it's telling us you are not covering all the cases. And if you don't cover all the cases, you will get some weird bugs. But you don't have this problem in Reason because compiler will tell you. So this is similar to lint. It will tell you your problem. And this is even more useful when you're refactoring. Let's say you were doing some refactoring and suddenly your exhaustive pattern matching won't be exhaustive anymore. Normally you won't have no idea. You will discover that when you run your code. But now, your compiler will tell you that your pattern matching is not exhaustive anymore. And again, if we compare this to JavaScript, you don't have insurance in JavaScript. If you have your if-else statements, you had no idea if it's exhaustive. And here you have insurance that your pattern matching will always be exhaustive. Now, let's take a look at the more complicated version of pattern matching. And here, just take a look that the idea is still the same. We have data, and we match them against patterns. And when we have a match, we return some value. In this case, it's the state of the game. Now, try just to think about how would you write this in JavaScript. Because in JavaScript, you would probably need to use many if-else statements and probably nested if-else statements. So let's take a look. Let's take this code and compile it to JavaScript using bucklescript. And as you can see, we have a switch statement and we have nested if-else. And just if you take a look at this, try to understand what's going on here, or try to refactor it. And you have no insurance here. You have no insurance if it's exhaustive. You have no insurance if it returns every time the same type. You have no insurance. And if you compare this to Reason code, here we define data, match them against patterns, and get the result. So we are telling compiler what to do. Just do this and get me a result. I don't care how you do it, just do it. But if we compare it to the JavaScript, to the imperative syntax, we are telling compiler how to do it, just telling it, try this, if this doesn't work, try this, else, if else. It's a really imperative approach. It's more complicated to read, and as I mentioned, you have no insurance that everything's really okay. Okay, I'd like to wrap up my talk now. So just a little recap. Why should you use React in Reason? And as I mentioned, Reason shares the core principles with React. And it's because first prototype of React was built in Ocaml, and Reason is based on Ocaml, so they share the principles. We have strong type system that provides us with clearer and safer code, superior to TypeScript and Flow, because it's built in and we have no runtime exceptions in production as a result. We have pattern matching, which is a really safe way how to process our data, as we just seen, and it's nicely declarative. And we have a lot of functional programming features. We've seen we have immutability out of the box. We have currying, piping out of the box as well. And we have also great separation between stateless component on the one hand and stateful component on the other. Because, for example, in React, when you define your component, you need to think class or function. But in Reason React, you just think state or not state. So you have the easier decision making. And also, in reducer component, you have this clear separation between side effects and pure state update. Now, if you are programming in JavaScript, it will be easier for you to get to Reason because of the JavaScript, of the syntax similarities. And if you've been programming in React, it will be even easier for you because you have all the React knowledge and the principles are the same, so you can start building stuff in Reason React and learn Reason itself as you develop. So to really appreciate the cool features of Reason, you need to try it for yourself. So get your hands dirty, try to build something with it, and if you don't want to install anything, you can try sketch.sh, and it's basically Reason Playground, so you can play with Reason and you don't need to install any dependencies. Now, if you have any question, criticism, observation, whatever, you can reach me via my blog or my Twitter account, or you can ask me questions after the presentation. Thank you very much.